right, let's get started. So I'm very happy to welcome Bjoern Hartmann from UC Berkeley today. And Bjoern is not only leading a super successful research group at UC Berkeley that has won multiple best paper awards at the leading HCI conferences, but he also directs the super new Jacobs Institute of Design at UC Berkeley, which is focusing on design education and also making. And this talk today is going to combine these both aspects, teaching and research for personal application. So, welcome, Bjoern.
Thank you, Stephanie, for that intro. So I want to tell you about interactive design tools for the maker movement. And while it's fun for me to fly around the country and give talks, I also, of course, want to point out that it's not me who's doing the actual work, but rather this lab of incredibly talented students and postdocs. So I'll make sure I acknowledge all their hard work right up front before we delve in. So in this talk today, I'm going to show you how new tools can help you rapidly create functional enclosures from 3D scans of sculpted objects, how new tools can help you debug breadboarded circuits by automatically finding and flagging errors, and how you can make an arbitrary 3D printed shape interactive by adding a camera as a super sensor. So these tools are all aimed at the growing ranks of the maker movement. So maybe we should back up first and start at the beginning. What is the maker movement? To me, it's what matters about the maker movement is that it's this bottom-up effort to engage people from all ages and walks of life in learning how the world of products and electronics and man-made objects works. Makers gain hands-on skills to actively participate in shaping that world rather than just consuming it. So take the electronics workshop in Detroit, shown here, and that's just a few miles away from the ruins of the Packard plant, kind of the largest ruin to a prior age of industrialization in the US. Makers include everyone from engineers to artists, and a key component is to be welcoming and open to newcomers, because for many it's the first engagement out of a passive consumer role. Maker Faire is probably ground zero of this movement. Maker Faire started in San Mateo. It started when I happened to be living half a mile down the road from the location, so I just walked into the very first Maker Faire. And it grew from 20,000 people at the first one to well over 100,000 now at flagship events, and close to 800,000, including all the spin-off events if you add them all up. Now, in addition to the Maker Faire and what happens in community spaces, maker spaces are also appearing in high schools and on college campuses. So this is a shot of my friend John Furlick's lab that he built at the University of Maryland. And actually, MIT knows a lot about this world of maker spaces. You just hosted last fall the first international symposium on academic maker spaces. Marty Culpepper in mechanical engineering is, I think, your makers are, and a very active figure in this community. So clearly, there's lots of interest at the grassroots level. There's lots of interest at the university level. But why does it matter, and kind of what is at stake? So I'll give you 3 reasons why you should conceptually care about the maker movement. The first is education. So I'll let you read this quote from favorite Bay Area philosopher Alan Watts.
Question?
Yes?
Does the word material here actually mean physical, or does it mean something abstract by that?
So he does mean working with things, with artifacts. It's not material design in the Google sense. So the interesting thing is that this quote is from the 60s, and I think if anything in the following decades we've only gone further down this path where I've seen graduate students in electrical engineering arrive at Berkeley, of course from other programs, never having built an actual circuit. So we may shortchange our students in our educational goals of actually knowing about the world. The second reason was articulated very well by Eric von Hippel, who is, of course, also here at MIT. and that is that many innovations come from extreme users of technology. So extreme athletes are the source of many innovations in sports equipment. Physicians and surgeons are sources of innovation in medical equipment. And so giving these users tools to better express their ideas for improvement in products can broaden our innovation pipeline nationally. The third reason to take the maker movement seriously is industry and the role of manufacturing and making things in our economy. So there was an interesting article, this is now also already a number of years ago, in Forbes, laying out why Amazon couldn't make a Kindle in the USA even if it wanted to. And so that is that we haven't just outsourced the machines that make things, but increasingly we've also outsourced the supply chain and all of the knowledge that goes around the making of things to other places, and that is probably not in our favor. So the last White House took note that the maker movement here may provide a corrective force to these three trends, and in 2014 the White House launched the National Maker Fair, which brought federal agencies and makers and other, so government and non-government together to clash and learn from each other. So there have been national maker fairs, makers have been invited to the White House. So maybe I've given you some arguments for why we should care as a nation about the maker movement, but there's another question, and that is, does the maker movement need us in this room as researchers? Well, you can guess what my answer would be based on the title of this talk. Some motivation behind that. I think what's interesting about making is that it inverts a traditional model of engineering education, which says, welcome, take some physics, some math, and then we'll tell you about circuits and signals and operating systems. And at the very end, once you have all of that, you put it together in some capstone before you leave. And making kind of turns it on its head and says, projects generate this pull for conceptual knowledge. I want to do something, and in the process of doing it, I'm going to learn about the concepts behind it. Maker projects also combine design, so the exploration, the specification of what something should be, and fabrication, the making it real. Something that often in industry has been specialized into different roles and is addressed by separate tools. So I find it really interesting that those aspects are combined. And makers now use this new digital fabrication tool set that gives them a lot more leverage than what they may have had in a kind of analog machine shop before. And fundamentally, I believe that amateurs, so people who are not doing something professionally, but who are also not total novices, need different abstractions and affordances in their software and hardware tools. And so it's the role of research to figure out what those abstractions and affordances are. And so I think all of these points imply the need for new appropriate design tools for makers. So an overall research theme for me is what should the 21st century workshop look like for this target audience of makers? And the term workshop is, of course, chosen for a purpose. So think back to the Wright brothers workshop, building the first controllable flying machines. And what did they rely on? Well, the equipment that they had gathered in their prior careers as bicycle mechanics and manufacturers. So these are the first power tools with a central spinning axle that goes through the workshop. Then, of course, there's Hewlett and Packard's garage in Palo Alto, just not too far away from where I live. And so it's the question of, what should be in the immediate environment around you that gives you more leverage to realize and build your ideas. So what does that projection forward look like? So for me, it's the combination of three different components that we now see. It's powerful design software, coupled to digital fabrication tools, coupled to ubiquitous, free, nearly cost-free programmable electronics in everything. Now, as Stephanie mentioned in her introduction, now the faculty director of the Jacobs Institute for Design Innovation, which is Berkeley's take at what that 21st century workshop should look like for our own undergraduate students. So this building opened a year and a half ago. If you've been to Berkeley's campus, just to the left of it, you see the patio of Soda Hall, the home of computer science, and just behind it, you see Etcheverry Hall, the home of mechanical engineering. So that gives you a geographic as well as an intellectual landscape for where we're located. We have 3.5 floors, where the upper floors are dedicated to flexible teaching studios, and the entire first floor is a makerspace that's open to all of campus, and then we have various specialized equipment labs sprinkled throughout the rest of the building. So here's a shot of the first floor makerspace. And, well, what do students do? What do they build in this space? Let me just give you a couple of examples. Sophie's Superhand was a project on DIY 3D printed prosthetics, so very much on the mechanical end of the spectrum, which, prosthetics that you can pull out of low to mid-range 3D printers, of course, don't rival in functionality what you can get in state-of-the-art medical prosthetics, but they have this unique benefit that they now can involve the wearer actively in the process of creating the prosthetic and get her to feel ownership and pride in it. Many of the projects are some flavor of what you would probably call IoT devices. So here is California. Up until a couple of weeks ago, we were in a multi-year drought. Right now we're drowning in rain and snow. And so here was a fixture level water flow monitor that students built. So you want to track who is using how much water in your home. Well, you do that with a water flow meter. You probably don't want to run a power cord into your shower, so how do you build the whole thing so it's self-powered? So here's a 3D printed impeller with magnets on the circumference. Water rushes through, impeller spins, induces a current in a coil outside that's just enough to power up a microcontroller. It takes a reading and sends it over Bluetooth to the phone that has to be somewhere in the room but not in the shower itself. Another example project, StepSense. The idea came from UCSF, our medical center, but then the students in our institute turned it into a real prototype. So sensory ataxia is a condition where you lose feeling in your feet. And so then you start basically walking open loop, which leads to falls, leads to lots of complications. This is a simple idea of sensory redirection. Whenever your foot falls on the floor, you send a radio signal like 3 feet up from your feet to your hip, where you wear cell phone vibration motors on your back, and you're able to reintegrate that new sensory information and say, oh, this is what a footfall now looks like, and people become remarkably more stable in their gait. Here's another. This is a device for firefighters that turns out in firefighting, all of the information flows out of the building to a commander that sits in a truck or an SUV. And so this is a device, a wearable device for firefighters that sends thermal imaging and regular imaging and gas pressure sensor, how many minutes each firefighter has left, all centrally out to a single interface. And so these are the types of projects that students, that a couple of years ago were maybe research projects in the ubiquitous computing literature, and nowadays, because of the tooling, students do these in 8 to 10 weeks. Kind of thinking about what happens at a higher level in these projects, it's the intersection of the 3 domains, right? Mechanical, electronics, and embedded software, as well as software living on tablets and in the cloud. And then as a human-computer interaction researcher, I, of course, care a great deal about the interaction that sequences how we control and have a dialogue with these devices. Okay, so this is the general domain I'm interested in helping with through research tools. And I think there are roughly 2 ways I found of being helpful. And the first one is looking at standard model of the design process. You take any design researcher, it roughly boils down to this process of first understanding, observing, and then going into this iterative prototyping cycle. Right? And so if we can just make this cycle of designing, externalizing through prototypes and evaluating that cycle faster, then you'll hopefully get to insights about what works faster. And so how do we make this cycle faster? We actually substitute technologies that are hard to work with technologies that are easier and faster to work with. And we lower the expertise threshold for experimenting in a given domain. So that's one way to help. I think there's also a second way to help. And that is, if you think about makers also as learners, as learning something fundamentally about the concepts involved in a domain, then they go also through a cycle of building something, reflecting on it, abstracting some generalizable knowledge, maybe through experimentation, and going through that cycle. And so I think we can also help by building tools that make reflective observation, understanding what this thing that you built is doing more successful. So teaching, explaining, investigating. All right, in the time I have today with you, I'd like to just share 3 different projects that lie at different intersections here. So I'm going to tell you a little bit about making enclosure design, prototyping of enclosures for interactive devices faster. Tell you a bit about helping you debug breadboarded circuits, and then prototyping the interactions one would have with the device that you build. So let's start with enclosure design. 3D printers have now been around for a couple of decades. Now that the patents have run out, they're found in many more places. Fundamentally, the technology is not new, and so you find them often in design studios to iterate on the look and the feel of a desired object. So this is a photo from Microsoft's hardware lab where you see prototypes for the ergonomics of a mouse or a new game controller. Now, however, a lot of these prototypes, they're just passive pieces of plastic. They don't do anything. If you want them to do something, right, then you suddenly jump into this world of electromechanical co-design where I'm designing the enclosure, but now I also have to think about designing the inside. Where am I going to put a circuit board? Where are the different sensors located? How do I mount them? How do I make sure they have the right distance? And so this tends to be tedious, time-consuming, very precise work that's kind of mismatched with the earliest stages of the design cycle, where you're just trying to see whether an idea is a good one or not. And you mostly do that in complex CAD software that has its own learning curve and certainly its own speed at which you operate. So we were motivated by thinking about tangible modeling. It's very quick to shape tangible, pliable material into a gesture of a shape that you might want to produce. But we also ran a study where we asked aspiring designers to sculpt enhancements, accessories for cell phones and other everyday objects. And what we would find is that people would often combine different representations. So they would take some modeling material and say, it roughly looks like this. But then there are actually these complex hinges that I don't really know how to express with my fingers and this modeling material. So I'm just going to draw a sketch and label that. Like a hinge goes here, a complex part goes here. So we were motivated by this observation to think maybe we can do something for this integration of shape and electronics that uses a similar combination of letting you sculpt the rough idea of the shape and then annotate what the functionality should be. So this is the Maker's Mark system. Roughly works as follows. We give you sculpting material and then a set of annotation stickers. So these are just little paper stickers that indicate where a user would interact with an object. And so the user would then model a shape and adhere the stickers to the surface. And now all these stickers correspond to electronic components. And so hopefully, the idea is if you author that at the top, can we generate the artifact at the bottom, which is a working enclosure where all the electronics fit inside, and you can kind of snap together a working object. So how do we do this? Well, we start as our input with this 3D object with stickers, and then we 3D scan the whole object, and that gives us geometry plus texture images. And basically what we then do is we find, using standard computer vision techniques, so SIFT features work just fine, we find all our stickers in the texture images, and we project them back into the 3D space, so we detect where on the 3D model all of these annotations are placed. Then we replace the annotation with a digital model of the component that tells us both about its size and that has meta information about how one would mount it. So how would you snap a component into an enclosure? And then we modify the 3D scan geometry by shelling it and punching through wherever we need clearance, adding mounting features wherever we need mounting features. And so you end up with a 3D model that is based on the scan, but that is modified to accommodate all of the objects that the user indicated with stickers. So to make that work, we need this extra metadata for the component, right? So we need its rough geometry, we need the clearance, and we also need mounting. And we just combine that to then modify the original model to add mounting geometry and controls. So then you can 3D print this modified model, and you just take off-the-shelf pieces and you just snap them in. And there's complementary research in toolkits for physical computing that has basically made lots of these components available, so you can just wire them together. All right, so the key idea here is that a maker expresses shape intent through sculpting and the functionality intent through placement of marks. So that works both for kind of I/O for the user. It also works for mechanical parts, like put a hinge here, or put a clasp somewhere else. The tool then handles the detailed geometry modification. And the one caveat is that it relies on this database of 3D component geometries. Now, turns out that may not be such an unreasonable assumption to make. So if you go to McMaster, who's ordered from McMaster in this room? Okay, at least half the room. So for the other half of the room, your standard, the biggest nationwide distributor of mechanical parts. And basically anything you buy from McMaster, down to a simple washer, now has a CAD model associated with it because it's value add for McMaster, right? If they give you that model, you're more likely to order from them than from some competing source. So there's kind of commercial incentive to build these metadata catalogs, which is interesting. All right, so project number one. Let me move on to, yes?
About that? So it seems like right now the user shapes their thing and the 3D scans it, and the user kind of doesn't get involved in any of that until they have a 3D printed thing coming out the other end. Have you looked at, I mean, what opportunities are there for them to fix in the 3D model things that they weren't able to do with their hands, like putting, I don't know, affordance textures, you know, this is the place where you're supposed to grip, this is how it should feel, maybe I should fix up some of the finger marks that I left on my model, just to take it a little step further beyond just the very first prototype to maybe something that you might actually end with user use for a few days.
So let me rephrase the question as, right now this is a single shot pipeline. Annotated object comes in, 3D print comes out. Many of our most successful design tools involve the user in an interactive loop. So one area where we've started to look into this is, well, what happens when what you annotate is physically impossible to create, right? Because you have interference between different parts. So they would crash into each other. There's not enough space on the inside of this object. And so now there's a question of what do you want to do about it, right? You probably don't just want to say fail, can't compute. But now you have to either start taking pieces out, or you have to modify the geometry in some way. And so we started to work on techniques that say, well, if we push this out in the back, right, that would create enough room to house all of these components, but it would also change the look. Is this okay or not? So ultimately, I think those techniques should then, they need to be in some design tool. The question is, what is that design tool? Because you didn't start out in CAD. You started physically shaping. So is it something that shows you this as feedback and then you physically manipulate the model, or do you just physically create the model once and then you scan it, create a parametric representation of it, and you're in CAD from then on? I don't really know yet. I think it's an open question, but a good observation that adding more interactivity in that loop is good.
A very quick follow-up. Have you guys explored augmented reality to use as an interactive way to potentially close that loop?
So the idea in augmented reality would be I'm now wearing some kind of headset and projecting additional information onto the object.
And then if I need to change something, it will show me how that would look, potentially overlaid on what I have.
Yeah, we haven't. So we've played around with augmented reality in makerspaces. I think one thing that's challenging is whenever you work with physical objects, the registration accuracy you need for it to be useful is quite different from the accuracy you need to play an enjoyable game. And so we haven't ventured too far down that path yet. Yeah, interesting idea as well. I'll show you some other augmented reality where we put the AR on the tool towards the end. Okay, so let me move on to project number 2, world of circuit debugging. So breadboards are kind of one of the great inventions of the 1970s, in that they really accelerated how quickly you could plug a circuit together. So actually a great advance. The disadvantage is that I think of them as a write-only medium. You assemble it, and then it's impossible to kind of, if you build anything of any complexity, to understand what it is that you built. So anyone in the room who has not breadboarded a circuit before? Okay, 2 or 3 hands. So breadboard has many holes, but underneath those holes you have connectivity. So horizontal rows are connected right until the middle strip. And then the power buses for power ground on the sides are vertically connected. So anything you plug into the same row gets internally connected. Right. Okay, so can you find the bug in this breadboarded circuit? It's right there somewhere, right? That wire came loose. So bread was very rapid to create, but different to interpret afterwards. And on top of that, they're not very mechanically robust. So if you put a breadboard on your self-driving robot, the robot bumps into the wall. Since it's all based on spring-loaded contacts, quite likely that something will pop out. And it's also just easy to miswire things on a board. So there's also, recently there have been some studies of students trying to create breadboarded hybrid software, hardware prototypes, and one of the outcomes of the study, which if you've breadboarded in hindsight is probably not that surprising, is compared to software, it's just much harder to identify at what layer the problem even begins, where the problem lies. And our hypothesis is that debugging is difficult because much of the state of the system is both hidden by default and it's difficult to examine, even if you know what you want to examine. So how do you examine? Well, you break out the multimeter and you take a point measurement. Or maybe you take out the scope and you take a point measurement, but over time. So a research idea is that point measurements require that you have a hypothesis about what the problem is. We know from studies that non-experts are bad at generating reasonable hypotheses. Like that is a skill that is acquired. And so how about we replace point measurement with ubiquitous instrumentation, where we measure everything all the time, and then combine some model of the circuit with the real-world measurements to diagnose and suggest where problems might lie. So here's the TOASTBOARD. It's the better breadboard. And we scan all rows, the voltage on all rows of the breadboard at about 200 hertz. And then we can show you the voltages directly on LED bars next to each row. We can also take that same information and show it to you in software. So here's now a virtual representation of your breadboard. And so if you end up scanning, then as you put your circuit together, you can see in real time that information updating. Now, just showing you the voltages is maybe already helpful, but we can be more helpful if we have some information about what the circuit is that you're trying to build. So there's a drag and drop interface where you can drag and drop virtual components now on this virtual breadboard. And once we have that model, we can now do automatic checks. So we can, instead of you discovering what the problem might be, we can check automatically what some common sources of problems might be and check whether the model, the real-world measurements are in accordance with that model or not. So for example, we can suggest that an LED you connected might be either broken or inserted backwards. Why? Because the voltage drop across that diode, in this case 3.3 volts, is inconsistent with what we would expect. And we can also just give you other measurements about your circuit. So here's that example in action. So a warning signs, just like in your compiler, right? The interaction model here is like the warnings and errors you get in IDEs. And as you correct the circuit, those warnings go away. Okay. Now, the other part where we can be helpful is if you work with ICs. Well, now there are other potential problems of errors, right? Did I connect to the right pins? What should the state of a certain pin be? Well, that information is found in data sheets. So, but you can take that information from data sheets and embody it in a virtual representation of that component. And so then, if you drop this op amp, right, we can already warn you, this op amp may not function correctly. Positive supply input is floating, connected to something. And you can also do things if you know the data sheet, right? So in this case, we're placing an ultrasonic sensor on. We can take circuit measurements and transform them into real-world values, like distances in a distance sensor, because we know the transfer function from the data sheet that translates the voltage into actual distances. So how is this built under the hood? So we have our breadboard, and then we connect the breadboard through a multiplexer scan chain to an ADC on an embedded microcontroller, and then we just round robin through all the rows one after another. We can feed that information either directly back to the LED bars or forward it to the software clients. So this is the custom PCB, and so basically what you do is you take the breadboard, you peel off the adhesive layer, and then all of those contacts are exposed underneath, and you take the breadboard and you adhere it to our custom board. Actually, a good chunk of the time of this project was spent on just figuring out how to get good mechanical contacts, so you get good measurements. There are two things we tried that work reasonably well. One is to use Z-axis transfer tape. So this is adhesive that has small conductive spherical particles embedded in it, which means it only conducts in the Z-axis and not in XY. So you just put a whole strip of that tape down and then put your breadboard on top. Or we also just have small holes and solder directly through the board to the breadboard. So the breadboard goes on top here. Microcontroller, just a standard off-the-shelf, $10 board, goes on the other side, and then we just have this scan chain of cascaded multiplexes so we can get to every row. And then finally, we have a pull-down network to get the voltages into a reading that the microcontroller can deal with. This actually, brings us, I'll just delve into one other small implementation part, is float detection. So a floating row is anything that is not connected through any conductive path to either power or ground. And what's the problem with floating rows? Well, if you don't know whether rows are floating or grounded, then if you show people information about the state of their circuit, it looks something like this. You're just basically adding lots of visual noise that half of this or 2/3 of this board looks like it's grounded when it's actually not. So rows look grounded to us. Sorry. Because we have this pull-down network that connects when we scan the voltage of any row. It's connected through this pull-down network that adjusts the voltage. It's connected to ground, so everything just reads as 0, whether it's grounded or floating. So how do we get around that problem? What we would like to have is something that looks much more like this, right? Where only things that are actively grounded are shown as grounded. Everything else gets filtered out. So we've come with a non-invasive float detection algorithm where we do one pass where we scan every row. If the reading is higher than 0 volts, well, then you have an actual voltage on it. Then we just display that. And then we do a second pass for everything that read 0 volts. We do a second pass where we now connect it through a pull-up resistor to voltage. And so if your row is actually grounded, you're still going to read 0. But if your row is floating, now you have a very predictable voltage that you will read at that pin. And so that gives you a nice way of figuring out where is nothing actually connected at all and where are you really grounding your rows. Okay. Now these checkers that I showed to you that show you warnings about diodes and different parts, they're just implemented in JavaScript, and there's an API by which others can contribute additional checkers. And that's a general pattern we try to build into our design tool, that there are always various user roles. So there's the end user, then there's us as the researchers or system authors, and oftentimes there's an intermediate role of experts who want to be helpful. How can you give them leverage to contribute expertise for the larger number of non-expert users? So in this case, the experts could be the one who extract transfer functions and other information from data sheets and embody them in these checker functions. So here, this whole tool is really about, not about prototyping, but it's about this reflective learning cycle, right? You build something, it doesn't do what it's supposed to do. Why not? How can I reflect and observe the state of the system and help the user conceptualize where the error might lie? Now, we're not actually going all the way here, right? We have some observation that something is wrong, but there are multiple different root causes that can lead to that same observation. And nothing in that tool yet helps you disambiguate which of the different possible root causes is at work here. Right, so a couple of limitations here. Right now you cannot supply arbitrary power. We all only work in kind of the 5 volt, 0 to 5 volt band. Populating those virtual circuits is cumbersome. Would be great if you could automatically detect what the components are. So I think that's an interesting research project in its own right. And it's also possible that we're now actually making the problem worse by overloading you with multiple possible warnings, right? And so that trade-off, I think we have to study more. So we're looking to deploy this in the classroom, and then the one thing I want to point out that's, I think, especially motivating, and that we've been working over the past couple of months, is not that many people build analog circuits in isolation these days. It's mostly you build a circuit to connect some sensor and actuator to a microcontroller so you can write some code and do something with those values. So how do you debug that joint system of code and hardware, and where the errors might lie directly at the intersection, or you don't know whether they're in hardware or in software? So I'll give you just a brief first sketch. Here's an environment that we've been working on where we instrument your circuit as well as your code, and we can show you behavior of lines of rows on your breadboard and of variables in your code, all time synchronized in the same way. And you can navigate at this point in the trace, where was I in the code? At this point that I wrote something to the console, where was I in the code and what happened in the circuit? And so kind of these principles from good information visualization environments apply to hardware-software debugging. So expect more on that in the future. The summary on the TOASTBOARD, what does it do? Ubiquitous instrumentation of user circuit that really lowers the effort of data collection. And then, so now we have that data, but we need to relate it to something. So you want to combine the data you collected with some, however, partial model of the circuit. We're not doing complete circuit nodal analysis. We're not doing simulation. Just kind of at the component level. Tell us where the components are. And so then we can, that allows us to provide debugging hypotheses preemptively. All right. Any questions on this project before we move on? Rob.
Yeah, I love this project. I love the idea of making visible what's going on in the breadboard, and thinking about this in relation to ideas from software engineering, which feels like you're bringing some of those things, like the checkers are, for me, assertions that you would have in a program. The other thing we have in programs is unit tests, right? We have ways and stubs, ways that we can carve out a module or even a collection of modules that are acting together and check them independently from the rest of the circuit, the rest of the program. That's incredibly hard to do on a breadboard, right? You have to pull out wires in order to make sure that downstream or upstream things are not messing up this component that you're suspecting right now. Have you thought at all about tweaking the breadboard, the very simple breadboard abstraction here, so that you can do that carving out without having to pull out any wires?
Yeah, So you're now giving me an idea of a breadboard where I can computationally change the pattern of connectivity.
Exactly.
Great, we should do that. That sounds awesome. So we've thought about something much simpler, which is not as cool, which is if you give us, I don't know if we need a complete schematic, but at least some notion of where sensors and actuators are connected to your microcontroller, we can automatically generate some code that only tests that single sensor, right? Or only tests that single actuator. And so we could run these unit tests of, does this peripheral that you connected, is it connected correctly? And I think it's really interesting to think of that in a user-in-the-loop way as well, where you may be able to measure some things, but maybe you also need someone to just look at the behavior and tell you what just happened when you ran that test. So that's something we've thought about, but I like that idea of dynamically rewiring the breadboard a lot as well. Yes?
Have you thought about basically trying to pull simplified models from SPICE rather than having to have this transfer of experts looking at the data sheet coming up with a transfer function, because those IO models already exist.
Yep. Yeah, so excellent. This is clearly something we haven't gotten around to, but it's already come up multiple times, that really leveraging all of the work that's gone into SPICE, into simulation tools, and into device characterization, right? We should leverage that here.
Because you don't need to do like full-time domain nodal analysis where you're looking at frequency response, but you're just looking at steady state.
Yep.
And that's computationally very easy to do. So
Yeah.
that could fit in.
Yeah, I fully agree. Yes.
I love the project, the prototype they're doing. It's great. I was wondering from a user perspective, like if you thought about what are some of the tools that makers are already using to document circuits. I was thinking, for example, about the multimeter.
Yep.
And I really like the fact that we have LEDs, but maybe we also have some checking for
Oh yeah,
circuit.
right.
And also, like you said, it can be cumbersome to go from what you're doing in C2 to a screen and back. And I know as a maker, I am reluctant to do that. So what are all the ways in which you can provide all the feedback locally with the lights blinking, with the sound, the combination of all these different outputs?
Yeah.
So you don't have to go to a screen unless it's super complicated.
Yes. So I'll tell you some things we've thought about but haven't built it. Is right now we're just reusing an existing breadboard. You can think about doing things like drilling small holes and putting fiber optics right next to each hole, and then coupling that to LEDs or a screen off-board, so you render all of that information right there in a location. I guess the question of AR comes up again. It actually turns out because breadboarded circuits are complex 2.5D entities, that rendering information on top of it is difficult because your reflectance and the base color changes millimeter to millimeter. So I think that actually is challenging. So we've been thinking more about adding more visual information right onto the board.
Right, but if you're trying to guide a user toward an assembly through stages, you have all of the signaling that you need there, right? If you just say this row and this row, hit a line, or if you want to put a
Right.
SOIC or whatever, different package in, you can say these 4 lines are going to be populated.
Yep.
So the user can be guided directly to that.
So let me riff off of one topic you just mentioned, which is assembly. So one thing I think that's also fruitful is if you know what someone is trying to build, you can lead them through a tutorial with this board and check step by step, and not just at the last step when there may be multiple problems interacting with each other. Excellent. So let me just, I'm looking at the time, there's not much left, so I'll briefly give you a sketch of, in 5 minutes, of the last project, and then I'll just open it up to more conversation with you. Okay. So, interaction prototyping. Let's return to this problem of integration of circuits and closures. And so our other intuition was, well, what if we just skip using all of the actual electronic components and substituting some other sensor for them? So here's the idea, is you take a camera, and instead of doing computer vision of the outside world, you do computer vision on the inside of a 3D printed object. So you embed the camera, and then as you interact with different affordances, joysticks, buttons, we pick that up. So the idea here is you're now in the world of CAD, you're creating a CAD model of your game controller, and then we add a virtual camera model right in CAD. So this is in SolidWorks. And say, I'm just going to attach my camera here. And so the idea is now when you move a button or a joystick, you can just use standard like blob tracking computer vision algorithms to extract all of that information without ever having to wire up an actual button or joystick. Except there's a little problem. And that problem is that cameras have a restricted field of view, and so by default, you're not actually going to see that much on the inside of an object. So, for example, here, field of view is that cone, and you only see 2 of the 6 interactive elements if you just stick a camera inside. So this is where we can now apply some smart techniques. So for example, I can take a button here, so field of view is in blue, camera is in green. And because I haven't printed the thing yet, I can still modify the geometry before I print it. Right? So now I'm going to propose the idea that we're going to modify the geometry before we print it to make the task of computer vision easier, which is kind of computer vision turned onto its head. It's not coming up with better algorithms to extract information from the world. It's coming up with better geometry to make computer vision easier in a known environment. So here's an example where we have buttons on every face, and we can just extrude all of them to the inside of the object so that a camera with a limited field of view can pick that up. In this case, that doesn't work so easily. Let's say you're parallel with the optical axis. Maybe I can come up with some complicated geometry, but we leverage the fact that we're dealing with makers. They like to physically work, and so we're going to borrow a technique from computer graphics, from ray tracing. So we shoot rays into this object, and then whenever they hit the boundary of an object, we're just going to reflect them by the surface normal and find rays that, after a bounce, hit the object that we want to see. Why might that be useful? Well, it turns out if you glue a mirror in that location, then all of those components become visible to the camera. And so the idea is you print your 3D object, then comes the highly technical step of increasing tracking accuracy, which is you take a Sharpie marker and you just mark up the ends of all these little extrusions that we printed.
How is it illuminated internally? Do you have an LED in there?
So the camera itself, we've put surface mount LEDs as a ring light around the camera. So you add the illumination when you add the camera. Then you glue little craft mirrors in at the places we indicate. And here's the camera with the ring light. You can see the LEDs right there. And you glue it on. And so then afterwards, you just do computer vision tracking, very standard algorithms, kind of off-the-shelf OpenCV of different interactive elements, such as this slider. Here we're using reflective tape instead of darker markers, but same idea. So different components now are associated with different vision algorithms. So here you're extracting location of a blob. With a trackball, you're extracting direction, magnitude of optical flow. But this is all very well understood stuff. So we've built trackball mice with it, and DJ controllers, harking back to my prior career as a DJ before I started grad school. And kind of other interactive devices that are not particularly tiny, so there's enough volume to embed this camera, but probably the technique could also be miniaturized. All right, so let me stop right there and just bring it back around. How do these tools help makers? Well, focusing on these two kind of conceptually distinct topics, right? One is about just making prototyping faster, even if that doesn't get you a robust, long-term usable artifact, but it gets you that artifact quickly. And the other one is just learning about the complex systems. The complexity is inherent in what you're trying to build. Understanding why things don't work and giving you the bugging aids. I think just as a future outlook, because you asked about augmented reality, so we're interested in a space of semi-automatic fabrication. Think of a spectrum of automation, a degree of automation and intelligence. If you go to Home Depot and you buy a hammer, there's no automation and no intelligence. If you buy a 3D printer, everything is automated. You make your model and you press start. If you buy a power tool, you get automation but no intelligence. You get a motor on a stick. And so what's in this in-between space? And here is one sketch. We've been working on augmented power tools. I think there's probably some resonance with the work of Amit Zoran, who was at MIT until just recently. So here's the first prototype of an augmented drill, where we add the kind of sensors you find in cell phones. So they're available at mass quantities very cheaply. Distance sensors, some computation, and some projection onto a tool. And that lets you now load instructions about the task you're trying to do right into the tool and project it while you're working. So here, the instructions say, drill a 12mm hole so we can track your progress. And off on the right-hand side, we can also track orientation, the orientation at which you're supposed to drill, and give you feedback whether you're, whether you're holding that 90-degree angle or the 45-degree angle or whatever else you're supposed to do. All right. This was a small slice of the work that my group does. We also work in other areas, in learning expertise sharing, interactive devices, and general UI tools and toolkits. So I'm happy to chat with any of you afterwards about any of those topics as well. And let me just close by crediting the students again. Thank you. Yes?
Thanks for your work. Great presentation. A lot of your projects look like products, and I wanted to see if you could comment on sort of this interplay, especially now with crowdfunding and the maker having their own economic footprint. Where are you going to evaluate your work as products in academia? What is the interplay that you see going forward in that space?
Yeah. So, good point. I think HCI work often can have the feel of being a product because you identify a user need and then build a system to address that user need. And then you have to build it to the point where you can evaluate it back with people. And so that is not so different from a product development process, except that the source of, you're pushing the envelope further, and the source of ideas may come from cutting edge technologies instead of things that are already proven out. Yeah, we've been thinking about, so things like the TOASTBOARD, right, that kind of lends itself towards productization because in there, nothing is particularly at the bleeding edge of technology where we don't know whether we could turn it into a product or not. So one of the limitations right now is in the projects I've shown you, we build 1 or 2 or 3, enough to evaluate in a lab study and demonstrate the benefits. It's been hard to align the incentives to afterwards then make 100 because the amount of just detailed engineering that goes from having something that you can deploy in a controlled setting to something that you can just mail out into the world. There's a whole world of pain kind of ahead there. I don't know. So Bunny Huang, MIT grad, writes very eloquently about the product development process and flying to Shenzhen and all the myriad different problems you then have to solve to make something robust enough to manufacture it even at small scale. And so I see in a completely research-focused environment, I think there's an incentive alignment problem where you're disincentivized to take that next step, even if it's very useful, because it'll just take a year or two in which the student who does that work, right, is not publishing anything else. For that reason, I think it's very interesting what the Media Lab is doing right now to put deploy into the mission. And so if it's the mission of the organization to not just prove out the research ideas, but also make sure you get credit for then transitioning them out. I think that's very interesting. So I'm really looking forward to see how that works for different efforts here. And I think we maybe at Berkeley have to learn from what's happening here. Or not? I don't know.
It depends what you're trying to achieve as an organization. Maybe if what you want is to be an incubation area for startups, and that's a great place. But if you want to be a place where you're doing research into interaction models and understanding what could be possible in that space, then maybe selling things is not the best way to evaluate it.
So I'll tell you, for me, it's a complete success if I'm in my group, we manage to write a paper that convinces someone else that they can start a company around that, and without our involvement, a year or two later, a 1995 or 9995 gadget sits on the shelf somewhere. I think I'm very comfortable with my job description as a researcher that it doesn't have to be me who takes that translation step. Now the risk though is that that translation doesn't happen.
Or
Right?
the risk is that industry partner has many more resources than you do to do those kinds of things. Like the last project that you showed with this augmented drill, Tactia, or now Shaper Tools, a company that came
Yep.
out of CSAIL, they just raised $12 million. Like, what are you going to do that in your user study research that's going to be able to compete against their A/B testing? You know, and how is that information, the things that they're learning
Well, but-
in user research, how is that ever going to come out into the broader research?
Well, but Shaper is a great example because Shaper goes back to a SIGGRAPH 2011 paper, right? That it was a SIGGRAPH paper, and that got the idea out there. And then it happened to be Alec who also incorporated the company because he knew the principles best. But now it's taken 4 to 5 years to get it out into the world, right? So that's, I think the reality that road is hard is just something to acknowledge.
I like your theme of taking software tools and putting them into hardware space. I consider software tools for debugging horrible now, but they may be better than
Right.
hardware tools. One of the underutilized tools in software is called a stepper. And I can imagine combining ideas from that guy into rewiring to have you step through the hardware process so that you're incrementally, say, conceptually adding a resistor and changing the voltage on the end of the line that you're incrementing. Something that I've worked on a lot with Henry Lieberman is a reverse stepper. So you might, instead of just incrementally building, start with the complete building and start undoing the build and then kind of go back and see where
So this
the
is
problem
Z-step?
might be. This is
Going
Z-step.
back to,
That's
yes.
right. That's
Yep.
right. So just it's an idea of
Yes.
capitalizing on your general theme and getting a little
Yes.
more leverage out
Yeah.
of it.
Yeah, so absolutely we're motivated by omniscient debuggers and how they can play out in this domain. Yeah.
Good.
Great. Yeah, I was wondering, for example, for your last project, you looked into conductive filament and combining conductive filament with non-conductive filament instead of using the camera, especially for knobs or buttons that can be very precise.
Yes.
And I was wondering if you see the example or if you consider in your work to use machine learning in the design of these processes, and
Mhm.
if you've seen any examples of projects that make use of arbitrary intelligence for digital fabrication learning.
Yeah, so answer to the first question is absolutely. Happens to be not my student, but Eric Paulus, who's another faculty member at Berkeley. His student, Kevin Tian, is very interested in, he has a whole library of different components where he 3D prints on the voxel-8 printer that came out of Harvard, where you have the ability to deposit conductive material as well as non-conductive material. One interesting challenge is mechanically the conductive parts are not that stable. So if you have a lot of contacts after 100 actuations or so, they'll just rub off. And so, but that's just another design constraint. So I think here the design constraint is how can you design interactive elements that are 3D printed where the conductive parts are never in actual direct contact. So you look at different ways of sensing. And the second question, for the role of AI machine learning. I mean, so I always like to use, for me, computer vision techniques fall into that realm. And so I've always been repeatedly, I forget that how useful cameras are and vision processing tools, and then I rediscover. I don't have a great example of other core AI, deep or shallow learning influenced modification. There's a lot of optimization going on in the graphics community, using optimization techniques to modify geometry to make it balance or to make it have different properties. So maybe that's kind of what Wojtek does here at MIT or Olga Sorkin at ETH Zurich.
All right, let's thank Bjoern again.